Just waiting for a few people. Okay, so we're gonna go. Thank you for being here. We're gonna talk about radio a bit, about IoT networks a bit too, and I mean, the objective is to give you some information about all this domain. You don't need to be an expert or whatever. I'm Paul Pinault. I'm working for a company which is Retour, and Retour is a engineering company. We do some stuff, basically devices and connected devices, and normally you may use some of our product, even if it's not our product, we are just a designing company. Like an Nespresso machine, for example, we designed 50% of Nespresso machine on the market. So that's some stuff we do. They are not connected. We do about 50 projects, and we're based in Lyon, Grenoble, and Clermont-Ferrand. So, but that's not the topic of today. One of the things I do is I'm part of Volcamp, which is another conference based in Clermont-Ferrand. You can get your ticket online. It's open. It's in October. A good conference too. And so waiting for last people. I'm gonna start talking with you about something which is Meshtastic, and the French version of Meshtastic, which is Gaulix. I keep some time to have people getting installed. Normally, during this talk, for the first time I give a talk, I have some time, so I don't have to rush. It's better to get a question for the end, but if at a certain time you're totally lost on what I'm talking, don't hesitate to raise your hand and ask a question. Would be better if you can follow. And that's going to be good. No question, you'll not get lost already? Okay, cool. Okay, so let's start. So what about a world where the infrastructure of telecommunication, electricity or whatever is destroyed? It's like really sad and maybe it won't happen. But if you look at a short past in Spain, for example, we had like 1 day without electricity. Okay, the only thing that was correctly working in Spain at that moment was the telecom, thanks to the battery and all that stuff. But basically, can happen. And yesterday, I talked with a friend which is in Texas and had trouble on a server. And I solved this problem on server and didn't understand why he had this problem. It's just because he had no water, no electricity, no telco since 3 days due to the flood that happened. So this kind of situation where the infrastructure is basically crashed can happen. And what I'm going to talk about is how we can continue to communicate in a such situation. Okay, that's not really motivating, even if there is big interest, but yeah, you don't especially like for building some things like this. So in this area, there is some interesting thing we can do, and basically what we're going to talk is also something that remind me my 16-year-old when I was doing a kind of radio arm, so CB in French, talking with people around me. And basically, we had a meetup every Friday with some unknown and random friends on parking, and we chat with other people that were about 10, 15 kilometers, and we meet people that way. So ChatGPT really likes the big antennas, but that's for fun. So I'm going to talk about how to do this in 2025. And basically, Meshtastic, which is the name of the technology I'm going to talk, is a way in this year and this current year to have out of band, so out of standard network telecommunication, and in French, because we like to have a local name, we basically name it Gaulix. So this is a topic of today. So let's go on some definition to understand this. Basically this, I mean, the name is Meshtastic So there is a term that could soon familiar a bit, which is mesh. So it's a mesh network. So what is a mesh network? Who know what is a mesh network here? Okay, it's not a lot. I think that most of you already use mesh. For example, who have a Wi-Fi with a repeater at home? Okay, some others. So that's kind of mesh. Sometimes it's also named mesh Wi-Fi. Who have a connected bulb, like IKEA bulb or Philips Hue? Okay, so this is Zigbee, and Zigbee is another mesh. So what is the purpose of a mesh? It's I want to raise a longer distance with a radio that has some limitation, and I don't want to deploy gateways or things like this everywhere. So basically, I will use a node as a repeater to transmit the information on a longer distance. So basically, in Zigbee, when you have a lamp, which is, I don't know, in a room, and you have your access point or your gateway, which is like 10 meters from this room, and you have another lamp, which is in English, le grenier. It's difficult to do this distance with the radio frequency. But thanks to the lamp that is in one of the room, you can reach this other lamp, which is in a grenier. So that's the idea of mesh network. And you have mesh network on different technologies. So you have mesh network on Wi-Fi, you have mesh network on Zigbee, you have mesh networks on BLE, for example. It's named WirePass, for example, or you have BLE mesh. So you have different things. So that's the technology we're going to use with a little difference. Because if I want to create a communication network with a mesh, if I use BLE, okay, I'm going to have a mesh of 15 meters for every hops. Okay, that's not really cool. If I do that with Zigbee, I have a hop of 300 meters. So that's not a lot too. And so if I want to make a network on a region, or eventually on a country, I need to have really longer hops. And Meshtastic is based on another technology, which is LoRa. Who knows LoRa or LoRa 1? Okay, great. Couple of you. So let's have a short deep dive on LoRa. So LoRa is a radio modulation which work on what we call a chirp. So this is a chirp. And what is a chirp is, so how does that work? Here you have the frequencies. So here we are on 869 to 0.4 to 869.5 basically. And on this frequency, here we have signal, what you see, and here we have time. Okay, so basically this is a way to see what happened in the previous seconds on the air and on the radio at this frequency. So this basically is a LoRa communication. Here you have a preamble. Here you have the reverse chirp that starts a message, and here you have the message, basically. So that's what you can see. And the idea is on LoRa, we're gonna have a, you see, movement in a frequency, going up, going down, and sometimes doing some wired thing. And this is the way we code the information. So based on the movement, we basically get a value, certain number of bits, and with these bits, we have a message, and we can decode the message. There is different advantage of doing this. The first one, if there is a noise somewhere in this frequency band, as we are crossing the frequency, basically we can avoid the noise. The movement still there. Even if you miss some moment, you see the movement. So it's really resistant to noise. That's the interest. And it's also, I mean, really able to, well, who you are with that kind of modulation, to do some really sensitive receiver. So it means that you can extract information even under the noise level. So that's quite impressive. I like this idea to explain this is, imagine you are in a lake and you have a rock, and you throw the rock in a lake, and you see the waves on the lake. So that's kind of radio frequency, but on water and visible. In terms of sensitivity for LoRa, imagine that you have a lake, which is like 10 kilometer by 10 kilometer, and you throw this rock in the middle of the lake, and you are on a beach of the lake, and you can detect the wave arriving. Okay, and basically the wave is really decreasing with the distance, and it's what you can do with LoRa is receiving this wave 10 kilometer from the source, so it's a really thin signal. Okay, so that's the interest of this technology, and basically it means that you can communicate over really long distance. And when I say long distance, it's basically about 30 kilometers, kind of basic distance you can get, but it can be up to hundreds of kilometers. Like the maximum distance is like 1,500 kilometers, something like this. So it's really long distance. Usually we mostly do like 20, 50 kilometers, which is already good, and a bit more on Meshtastic. We're gonna see why. Okay, I don't want to go a lot in details, but basically, in fact, you see there is some different movement, and inside the chip, there is a system to transform this movement into levels, and levels are basically corresponding to values, and values is encoding information. There is a, we're gonna detail a bit this point after. There is a parameter in the modulation, which is the spread factor, and there is a number behind the spread factor, and it means that on SF7 you encode in one chirp 7 bits, and SF12 you encode 12 bits in a chirp. That's basically how it works. So we have LoRa. LoRa is a point-to-point communication. So LoRa is a kind of equivalent of Wi-Fi, totally working differently, but your Wi-Fi solution system or Ethernet, okay, it's in the OSI model, a level 2. So it's a point-to-point communication system. So LoRa is this. So in practice, it works quite well. That's the first test I do with LoRa and LoRa 1 in 2014-15, something like this. And I put a gateway on a mountain. It's on Clermont-Ferrand. So it's on a mountain. And basically, I walk into the street or drive into the cities. And all the points you see there are points where the network is passing. So it's a coverage test. The objective is to see, I mean, first test I did, so, okay, it's supposed to be good. How much is good? And what the limit you see there, I mean, if someone knows Clermont-Ferrand, the limit there is mountain. So basically, the technology is not able to pass through the mountain. The mountain stops the signal, as in many situations in radio. So everything visible is covered. So here we are about 11 kilometers in this direction, 8 on this direction. It's smaller because there is lots of mountain there. But yeah, it's really means that with one antenna, one gateway, you can provide connectivity on a whole city. And more, because here I didn't drive faster than this. If we look at payload, I won't go in detail for this. Just what I want to say is that on a payload, you have a standard frame with a header. So it's radio, it's whatever, but it's like what you have on Ethernet or anything like this. Maybe one of the difference here in this payload, you don't have an ID like on Ethernet. You're gonna have a MAC address. You won't have this on LoRa at this level. And what is important for me here is that there is a payload in this standard LoRa frame, and on this payload you can implement any protocol. So you can, I mean, you can do TCP/IP. No, it won't work really. It's not made for this, but you can have different protocol over LoRa, and Meshtastic is one of the protocol you can have over LoRa. Some numbers, quite old. I didn't have time to refresh it, but just to give you an idea, LoRa in end of 2023 was about 240 million of devices compatible. Now it's more about 700 million. something like this. I don't have the exact number, but it's more that's ID. That's for the devices, and for the gateway device we won't use in Meshtastic. It's more like 6 million at this period of time. Just to give you an idea, if this gateway were correctly placed over the territories, this could cover like 18 times the planets where people are living. So we don't need to put this in ocean. So if you put this on just on state, Earth, you get like a big coverage. The reality is totally different, but it's what you could get. So this to say, so we have LoRa. In LoRa, we can have different protocol, and one of the most famous protocol is LoRa 1, which is a way to use LoRa in an infrastructure environment for having industrial communication or public networks. So who already used LoRa 1? Some? Yeah, some. Not less than people that have heard it. Okay. So LoRa 1 is an infrastructure network. So basically means that we have device, we have gateways, and a communication sent by one device is received by all the gateways around. And the gateways are connected to what we call a LoRa network server, which is basically a server in a cloud, usually. And this server is basically processing the protocol, extract the data, and push the data to your application. So that's the idea. So this is really an infrastructure network. So even if this device is working on battery, even if the gateway usually have some backups, energy backups, and network backups, it's rely on network connectivity, and this server is on a cloud and rely on an infrastructure. So this is good, really working well, but it rely on infrastructure. So let's come to Meshtastic. So Meshtastic is just another protocol running over LoRa with the purpose of working without any infrastructure. That's what it is. So let's have a look on what happened in the frequency and what is the best frequency we can use for running such system. This is, I mean, in the frequency, you cannot do exactly what you want with on the air. There is some restriction. In particular, I mean, there is a emergency service or military that use some frequencies, so it's not really good to use them and transmit on this frequency. And so if you want to play without having to pay a lot for having a frequency, you have some frequencies bands that are called ISM, which are, I mean, free bands you can use. So you may use a lot, in fact, of this frequency, maybe without knowing it. One of the most used is the 2.4 gigahertz. So that's the Wi-Fi, Bluetooth frequency. Also Zigbee is on this frequency. There are good frequency. For one good reason is that the same frequency can be used everywhere in the world. So that's really cool when you are doing devices with this. There is some limitation of this frequency is the distance you can get. In fact, higher is the frequency, and basically lower will be the distance, and for one specific reason, which is you won't be able to pass through walls, for example. And another frequency that is well known is 5 gigahertz, which is also used by Wi-Fi. And to, I mean, one of the big interest of 5 gigahertz is when you are in a flat, every people have a different Wi-Fi, and you create a lot of collision when you are using the same frequency. You don't really see it, but if you look at it, you're going to have a lot of collision. By using a 5G, you will have lots less collision, not because it's 5 gigahertz itself, it's because the 5 gigahertz won't pass through the wall. So basically, the signal of your neighbor will be really lower compared to your signal, and so you won't have lots of collision. So that's better for many this region. But now, if you have a big house, it's better to be on 2.4 gigahertz because you will have more facility to pass through your walls, and you won't have any impact of the neighborhood because they are more at a longer distance. So at the opposite, on the frequency that are free, you have 169, which I mean is a really low frequency, and this is really good to pass through wall and eventually go deep. So it's a frequency that is used for metering, like water meter, electricity meter, and that's kind of thing. The problem of using low frequency is that you need big antennas. It's the size of antenna is also related to the frequency. So it's like 2 centimeters for 2.4 giga, but it's more like, and I'm not sure, something like 1 meter around for 169. You can for sure reduce a bit this, but it's a bit complex in terms of design. So two other frequencies that are used, 433 megahertz, really used in garage, cellar, or sorry, portail de, okay, remote portal opening, basically, or this kind of thing. And the last one I'm interested in 800 megahertz, 868 megahertz, which is the most commonly used for IoT communication. You have also a lot of a sensor like your temperature, wireless temperature sensor usually use also this kind of frequency. So in 868, in fact, the real band is between 865 to 870. So 868 in the middle. And in this frequency, you have different sub-bands with different rules. Because what's important when you want to share something is to create rules for making sure that there is no someone who is taking all the bands, all the common bands for himself. So in 2.4 gigahertz, for example, there's no real rules. So you can use the band 100% if you want. It's legal. So basically, you can jam your neighborhood if you want. There's no illegality on doing this. Not really good, but you can do that. In X68, there is some rule, legal. If you don't respect the rule, you can go in jail, pay a lot of money, and so on. I never see someone in jail for 868 noising, but jamming, but it can happen. And if we look at this band, which is the most common for IoT, there is two rules, in fact. One is the power you can use. So it's 25 milliwatts. And the second one is a duty cycle. So it's basically the time you are authorized to talk during 1 hour compared to the time you need to shut up during this hour. So with 1%, it means that you're allowed to emit for 36 seconds over 3,600. Okay? So that's the rule that are there. Just a point here. So 25 milliwatts. When I say that LoRa is capable of having 1080 kilometers communication, it's at this power, which is really, really low. I mean, your smartphone is more like 2 watts, between 250 milliwatts and 2 watts, depending on the distance to the antenna. So here it's 10 times less, basically. The advantage is that, I mean, it does not drive the battery. So you can have long distance, but also a really long autonomy, like a decade on a battery, which is the interest when you have an IoT which is lost somewhere. So there is another band here that is interesting for doing mesh. And this is the one that is used. Here's this band. Because this band in X69 is allowing 500 milliwatts. So it's really more than the 25 milliwatts. And you can go to 10% duty cycle. So the 500 milliwatts are interesting because instead of achieving like 10, 15 kilometers, we're going to be able to achieve something like 70 kilometers with the same device, just boosting the transmitting power. So if we want to do a network that is regional or national, we need to get longer distance. So that's interesting. And the 10% duty cycle is really important because we are a mesh. So it means that when I'm going to receive a message, I have to transmit the message, even if I don't want to talk myself. So the number of transmission will be higher. And I need a higher duty cycle if I don't want my network to shut up at a certain time just because we have a limited things. So 10%, let's have an idea of what does that mean in terms of number of messages, because 10% say like this, not really interesting. So let's back a bit on the spread factor. I told you previously that there is a parameter in LoRa named the spread factor that defines the number of bits we are transferring in one chirp. So SF7, I transfer 7 bits. SF12, I transfer 12 bits. But as you can see here it's time. It's not just a question of number of bits I transfer, it's also a question of speed of the transfer. And in fact, in this mode, SF7, I will be able to transfer like 5.4 kilobits per second, when in SF12, I will be able to transfer only 250 bits per second. So it's very different. But there is a side effect which is interesting. In that mode, I can go really far compared to that mode. It's more like here, I can reach like 80, 100 kilometers. And here, it's more like 5 to 10 kilometers. That's, yeah, an idea. Even if this really depends of the antenna, radio run, noise run, and so on. But it means that the time for transmitting a bit is different, and so it impacts the duty cycle. I can send less bits with 1 or 10% on that mode than on that one. So concretely speaking, imagine I want to transfer 10 bytes of data. This slide has been made for LoRa 1, so yeah, the numbers are not exact, but it gives ideas. If I want to transfer 10 bytes of data in SF12, so 250 bits per second, it will take about 1.4 seconds to do that. And if I do that in SF7, it will take 56 milliseconds, so really faster. And if I look at what happened with the duty cycle, it means like in 1.5 minutes, I can transfer only 6 messages. So it means that on my mesh, if I have to retransmit message, it means that here I can only retransmit 6 messages over 90 seconds. Can be okay, but can be a limitation. If I go to SF7 in 1.18 seconds, sorry, I will be able to transmit like 162 messages, which is basically huge. Okay, so we will prefer to use lower SF than higher SF for doing a mesh, and usually we'd use something which is in between the two for having a good compromise in between bit distance and ability to scale. Okay, I'm basically finished with a deep dive into LoRa and that stuff. You okay? Okay, no one lost. I'm not finished, but no one lost. No question for making someone surviving and going out of the floor. Okay, okay. So, Meshtastic. So Meshtastic is based on all of this, and Meshtastic is a community which currently, I mean, it's hard to estimate really because the problem is without infrastructure, so it's hard to count devices. But it's something like 50,000 devices, so 15,000 nodes that are connected to this network over the world. So it's a big success, basically. We can have some maps because we will see that to join the different sub-network, we have some infrastructure we can use. So this helps to count a part of the device, but not all. So basically on the maps, we can identify something like 20,000. But if we look at the number of devices that has been sold, it's more like 50,000 devices deployed. So it creates a network based on this. That's global. The mesh network can be used for different usage. So we talk about the disaster, which is the starting point of Meshtastic. I also noticed that it's interesting for doing social, just discussing with people and for hobbyists, basically. But there is lots of different applications because, in fact, it responds to some specific point when you have vast area to cover, when you have things that are moving. So what you want to where you want to get the data is not at one identified place, but moving everywhere, and you cannot deploy the infrastructure or move the infrastructure in the same way. And when it's impossible to deploy infrastructure. I have a good, I mean, from my point of view, the best example for this is military. When you are in a battle on a field, basically you have vast area to cover. You are protecting your country. It's really vast. It's moving every day. It's the front is some kilometer above or behind, and you cannot deploy infrastructure. I mean, if you do that, the enemy will start by destroying it. So mesh network is very interesting in this context, for example. But there is more sympathetic situation, like if you want to track wildlife is moving and generate together. So you can use like a wolf to communicate with other wolf to reach one point of the infrastructure to get information. Agricultural is moving, and ocean is interesting. You have moving things, the boats, and you cannot deploy infrastructure in the middle of the ocean. So you can use satellite, or you can eventually do mesh. So plenty of application. How does that work? Let's go to explain. So there is plenty of way of doing mesh. Okay, here I'm gonna explain how Meshtastic is working, and that's interesting because Meshtastic is like a KISS, mostly stupid and a bit simple. Okay, and there is plenty of other solution on mesh that are really more clever, like making trees and optimizing the route and so on. But on Meshtastic, there's a really no, I mean, yeah, I don't have the word, but it's really simple and stupid. And the objective is to be able to run it on lots of really simple devices, so you don't have a lot of memory and so on. So how does that work? Imagine, so here I use tower. It's a bit not good. In fact, just imagine that in fact it's a such device, so it's a device. It's not a gateway. So imagine you have a device. It's AF. Sorry, I have to right direction. Yes. So we have one device. It's AF19. Okay, they have a name like this. And you want to send a message to BC30. And you use a parameter, and this parameter is the maximum number of hops we're going to have. It can be up to 7, but here I set it to 2 for my example. And so basically, this device is going to start looking at what is on the air. If no one is communicating right now, okay, he can talk, so he's going to send the message. And the message is received by all the nodes that are around, so like 1 or 5 kilometers around. And so we have 2 nodes, ABO5, AC12, that receive the message. And basically, as I say, the purpose is that they will repeat this message. But if they do it immediately, we're going to have a collision. Okay, so we don't want the 2 nodes to communicate at the same time. So basically what they're going to do is they're going to sleep a bit in a random time. So one of the other will sleep, will wake up before the other one and will send the message. Okay, that's interesting, but that's not really good because in fact we can imagine that ABO5 is just like 5 meters from me when AC12 is like 1 kilometer. So it would be really better if the message is repeated by AC12 more than ABO5. And so in fact, the time a device is going to sleep depends on the signal strength at the reception. So as this one is at 1 kilometer, the signal is lower than this one, and so it's going to sleep less than this one. So he wake up first. And so as he wake up first, he's going to send the message. When I say that the device are sleeping, it's not really true. In fact, they are listening. They are listening if someone else already repeated the message. So when AC12 will wake up and send the message, in fact, ABO5 will hear it and so say, okay, it's repeated, I don't have to do it. So the message won't be repeated infinitely between the device. So this is what's going to happen. So AC12 will send the message, will repeat it. So 2 new devices will get the message. It decreases the hop. So hop is now 1. ABO5 gets the message repetition. So basically, it won't repeat it. And AF90 also receives this repetition and basically knows that someone repeats the message. So we don't know if the message has arrived, but it already knows that the message has been received by someone. Quite interesting. You are in your house, there is a flood, you have no other way to to send a help message to someone. At least here, you know that your message has been received by someone, even if it's not the destination. Okay. So now we have two new devices getting the message, and so they have to repeat it. Okay, same scenario. But in this scenario, so AC12 is like 1 kilometer, and ABC is like 500 meters. So normally, this one should send the message. But this one is a router. So in Meshtastic, there are different roles, and based on that role, you can get some priority. So you just declare your device as a router. So it's, I mean, no real decision behind this, just the owner of the device who decides this. But basically, if you declare your device as a router, it means that you have installed your device on the top of a hill or on your house with the antenna, big antenna outside. And so basically, this device eventually is able to propagate the message like 10 kilometers. When this one, which is a client, can be in my pocket, can be just a few hundred of meters. So the network will give a priority to this device. And so this one will sleep really less time than any other client. And this is the one that will resend the message. So this one receives the confirmation. This one receives that someone sends the message, so we don't have to report it. And we have up, which is now 0. So the message won't be repeated anymore. And it's sent to client BC30. So that's my target. So we're really lucky we have been able with the 2 apps to reach our target. And we also have client 4242 that receives the message. So here basically 4242 could send again the message because he don't know that BC30 received it. But in my example, as hop is 0, he won't do it. But in practical, I mean, if the hop would be 7, potentially he can send it another time. Okay. You're good with this? Cool. So that's really great. But basically, we have 7 hops maximum. And I say that, I mean, if we have router everywhere with big antenna, we can basically do like 700 kilometers, but that's it. Okay? So how to make a global network if we cannot get more than 700? You put a bit of infrastructure, and that works. So in Meshtastic, you can have nodes that are also connected through Wi-Fi to internet, and they connect to MQTT server. And so you can have a message reaching MQTT server, and the MQTT server is connected worldwide, so your message can be propagated worldwide, potentially. So this needs an infrastructure. So if we look in terms of disaster and so on, if the disaster is global, yeah, this not work. You can just talk with the people around you. But you can also consider that if the disaster is local, like flooding, earthquake, or these kind of things, if you can reach like 700 kilometers that way, at 700 kilometers, you can find something which is still there and with an infrastructure and propagate your message. So that's quite interesting. The most interest of this is more the social aspect. I mean, in Clermont-Ferrand, for example, I think I'm alone or quite alone. Even if I placed a lot of devices and there is a good coverage, there's no lots of users. So if I can just talk with myself, it's not really interesting. So thanks to the MQTT, I can talk with people in Lyon, in Strasbourg, in Britain. Basically, it works well. So that's interesting. Okay. Just what I said previously, we have the LoRa frame here, and we have its payload. And basically, Mestastic is a protocol which is inside the payload. So it's do not break anything in LoRa. It's just one protocol over LoRa. what I can just tell on this is basically Meshtastic is really not made for going to industry. It's really a thing for hobbyists. The protocol is really badly made. The security is badly designed. I mean, in the code, they mix all the services with the protocol, so you don't have a separation between the layer 3.4 and the layer 7, if I talk in Aussie model. So it creates lots of limitation. I did not notice that, sorry, but you have QR code everywhere. They are related to some blog post or video I've made on this topic if you want to go deeper. Okay, so I mean, the protocol is a bit complex. It creates big messages, but it works well. Okay, for hobbyist activity, I don't recommend it for industrial activity. How does it work? In fact, it's interesting in terms of hobbyists, really bad if you want to implement something in an industrial point of view, but you have a lot of service that comes with a stack. So it's not just a network protocol, it's also a lot of application. And so you have services out of the box, like chatting, which is the main purpose. So here is the example of different standard channel we have on Meshtastic, on Gaulix, sorry. So we have balise, it's more send telemetry information, blah blah, to talk about anything, and tech to talk about the technology itself. So they are like ERC channel, basically. So you can say what you want. But you have different services that are basically in the stack. So like coverage test, counting people, different telemetry we have there. So this is, configured by default. And what is really interesting in Meshtastic, and this is the reason why you get like a 50,000 device, is because it's really accessible to people. In fact, it's hardware, it's radio, but you just have to install it on a device, and you do everything with a smartphone. And your smartphone don't need to have a GSM subscription or LTE subscription. You just need the smartphone as a device, and it's used Bluetooth in between the device and the smartphone. It works on many devices. That's another reason of the success. It's because it runs on device that just costs $20. And in fact, it mostly works on device that most of the hobbyists have at home. Because in fact, we bought this kind of device. Have one here, one other here, and one other right here. We bought this kind of device for hacking stuff on LoRa, and you have plenty of them, and you don't have application for all of them. So for Meshtastic, you take them, you just flash the firmware into it, and you are on Meshtastic. So there is 50 more devices that are available on the market that can be used for Meshtastic, and it's quite easy. Once you get your device, you can install it, as I say, as a router or repeater on your rooftop, or you can just use it as a device you have in your pocket, so in client or client mute, which is a client who does not repeat, to be participating for the network. And so let's come to Gaulix. What is Gaulix on Meshtastic? Meshtastic is a global worldwide network, and Gaulix is a French community. In fact, in Meshtastic, you have plenty of parameters you can set. The MQTT server, for example, is a parameter. There's no global MQTT server. The radio setup, like the spread factor, is also something you can set. And so basically, if you set random values, you will only talk with people who have the same random value that you have. So if you want to do something more working well, regionally speaking, it's better to set up some of the parameters, like the MQTT, like the radio settings, and so on. So basically, this is Gaulix. Gaulix has defined some standard to be used in France. And here you see the device that are deployed. So there is some around, apparently. And what you see in green here is the confirm links. So basically, the purpose will be to be able to have green line everywhere to mix all the network. But for example, you see that Clermont-Ferrand here, even if we have some devices, they are not linked to others' devices. So we cannot really communicate, but through MQTT, we can do that. So how to be on the network? First step, you get a device. So $20 on AliExpress, Amazon, or whatever, or maybe you have some. You you select the device, you select the firmware version, basically the last stable, and you can flash, and it's directly on your browser. So you have nothing to install on your computer. Everything is working on a browser. So that's really cool. Once the device is flashed, you install the Meshtastic application on your smartphone. You will see your device appearing here through the Bluetooth connection. You select it. Basically, you have to select the region. So we are in Europe, so 868 megahertz. And then you go on Gaulix website and you flash a QR code, which is a configuration QR code. And so automatically the setups will be made on your device. The device is restarting. You will see there's different channels appearing, and so you can start talking with different people on this channel. If you have a friend, you can create your own channel. There is a shared key in between, and so you can have a private communication with a friend, for example, if you don't want to be public on this. You also have to create a name. There is a small app for doing this. So for example, one name for me is 63, so that's my department. Clermont, which is my city. The setting, radio setting I use, long moderate, 8, I'm not sure. And the CL, I'm a client. So you have a name for identifying who you are. And basically that's it. So if you have some question, don't forget to register on Volcamp. If you have some question, we have like 1 or 2 minutes. Yeah. Because the protocol itself is not really secure. That's one first point. In fact, the problem with the security is that you have encryption, but the key is also used for doing some masking with the channel name. And so basically, this is throwing some part of your shared key. So in my point of view, there is a risk on that side. So that's one reason. The other is that the code is really linked with the application and really complex, so it's really hard to just extract what you want. And if you use this into an industrial project, it's going to make a lot of complexity for something you don't need. Yeah. So and the other reason is that it's not really scalable. In fact, you have a risk of scalability you may not really control. And the last one is, in my point of view, the way the routing is working does not guarantee that your message will reach. Like imagine you have 2 valleys, and so your message goes on one valley because it's a smaller signal, and it will never go on the second valley. That's yeah, there is some different thing like this. There is others LoRa mesh that are more ready for industry, like Oramanet, for example, which is more interesting for this. After you can, I mean, some people do this, but myself, I won't do this. Yeah. In terms of bandwidth limitation, you mean the size of the bandwidth, or the okay. Yeah, not megabytes. So as I say, if you go SF7, you can go up to 5.4 kilobytes per second, but you have to apply the duty cycle. So as you can only use 10% in this bandwidth, it means that it's more like 540 bits per second and not 5K. So yeah, it's really under 1 kilobits per second. So don't transfer images, forget to transfer soon. Yeah, it's really telemetry, GPS localization, SMS equivalent message, this kind of things. Okay. Yep. There is different way to do location. The first one, the signal strength, so RSSI, it's really not good. Basically, it's more like you can say, okay, you're north of a city or south of a city. That's basically you can get with RSSI. Sometimes you have a bit more. If you are really close, you can be more precise, but it's really bad. For precision on LoRa, you can use what's it, TDOA, so time difference on arrival. So if you have clocks that are really good on gateway, so it's more for infrastructure network. But if you have gateways that are really well precise in terms of timing, you can measure the difference of time, and it's like a GPS basically. But the limit is the signal in LoRa. You cannot really filter the echo compared to the signal strength, and so in fact in a city, your precision won't be good because all the echo on buildings, so the distance becomes bigger even if it's could be straightforward, and so the precision in city is more like 500 to 600 meters. So it's not really good. And after you have some other techniques, but you never be under 100 meter for a location with LoRa. So I mean, 100 meter is really good. Even 300 meters is really interesting, but you can track and follow someone. You need a GPS if you want to have a precise location. You put a GPS on the device and you report this information. Yeah. Thank you. If you have a question, come to see me. And
just for those who want to hit soccer, there is a two line inside and outside the building.
if you want to see also how it works, I have devices and the application. We can also have a look.